Hi, this video I'm going to tell about the various recovery system used in DBMS. First, I will tell about the failure classification. There are different ways the system can fail. First one is a transaction failure. So transaction failure is divided into two types. One is a logical error and other one is a system errors. So logical error means transaction cannot complete due to some internal error condition. That is a logical errors. System errors means the database system must terminate an active transaction due to an error condition. So normally whenever a deadlock occurs, your system may crash or system may terminate. So that kind of error is called as system errors. Second one is a system crash. So system crash means due to power failure or some other hardware software failures causes the system to crash. So what is the assumption we make here is that is a fail stop assumption. Non-volatile storage contents are assumed to not be corrupted by the system crash. There are two types of storage we have. One is a volatile storage and other one is a non-volatile storage. So whenever a system crash occurs, non-volatile storage contents are assumed not to be corrupted by system crash. And third type of failure is a disk failure. So disk failure, head crash or similar disk failure destroys all or part of the disk storage. That type of failure is called as disk failure. So there are different recovery algorithms are available. So what is meant by recovery algorithms means these are techniques to ensure database consistency and transaction atomicity and durability despite the failures. So recovery algorithm normally two parts. One is action taken during the normal transaction processing to ensure enough information existing to recover from the failures. Whenever a failure occurs, what are the actions we take during the normal transaction processing to ensure the enough information are available? That is the first one. Second one is the action taken after a failure to recover the database contents to a state that ensures atomicity, consistency, and durability. So these are the different types of storage we have. First one is a volatile storage. It does not survive system crashes. Whenever the system crash, whatever data that is available in volatile storage, that won't be available. So examples, so the data available in main memory as well as cache memory, whenever any failure occurs or system crashes, whatever contents available in main memory and cache memory will not survive. That is a volatile storage. Second type is non-volatile storage. So non-volatile storage, even though the system crashes, the data may survive. Examples are disk storage, tape, flash memory, non-volatile RAM. And other storage is a stable storage. It is a mythical form of a storage that survives all failures. This is approximated by maintaining multiple copies on distinct non-volatile media. These are the various storage structure and how we can implement the stable storage. So stable storage, as I told, we will maintain multiple copies on distinct non-volatile media. How we can do that is we can maintain multiple copies of each block on separate disk. Copies can be at remote sites to protect against disasters such as fire and flooding. In case a failure occurs during the data transfer, can still result in inconsistent copies. What may happen is the block transfer can result in, there are three cases. One is successful completion. Whenever we are transferring data as a block, it may successfully completed. Second one is partial failure. Destination block has incorrect information. Some part of the block may be delivered to the receiver, and total failure, destination block was never updated. And protecting storage media from the failure during data transfer. These are the solution whenever the partial failure or total failure occurs. We can execute output operation as follows. Assume that there are two copies of each block. Write the information onto the first physical block. When the first write successfully completes, write the same information onto the second physical block. The output is completed only after the second write successfully completes. And copies of the block may differ due to failure during the output operation. To recover from the failure, first find the inconsistent blocks. So inconsistent block means either the transfer may be partial or the total failure. So there are two different solutions we have. First one is an expensive solution. Compare the two copies of every disk block. As I told, we are storing in two physical blocks. Okay, we are comparing both copies, comparing two copies of every disk block. And another better solution is record in progress disk writes on non-volatile storage, and use this information during recovery to find blocks that may be inconsistent and only compare copies of those instead of comparing all two copies of every disk block. So whichever information that is inconsistent, that alone we are comparing. So normally it is used in RAID systems. This is for finding the inconsistent blocks. So if either copy of an inconsistent block is detected to have an error, overwrite it by other copy. If both have no error but are different, overwrite the second block by the first block. These are the different data access. Normally physical blocks are those blocks residing on the disk. Normally in disk, blocks are stored as physical block, and other one is a buffer blocks. So buffer blocks are the blocks that are residing temporarily in the main memory. Two blocks I told, one is a physical block. So physical blocks are residing on the disk, and the buffer blocks are residing temporarily in the main memory. The block movements between disk and main memory are initiated through the following two operations. First one is an input operation and second one is an output operation. So input operation transfers a physical block B to main memory. Normally physical blocks are residing in secondary memory, that is a disk. So input means we are transferring the physical block into main memory. Output means transferring the buffer block B to the disk and replace the appropriate physical block there. So each transaction, so we may call this one as a transaction. So each transaction Ti has its private work area in which local copies of all data items accessed and updated by it are kept. So normally we perform read and write operation. So transaction transfers the data items between system buffer blocks and its private work area using the following operations. One is a read operation and the other one is a write operation. So read operation, read of X, assigns a value of data item X to the local variable Xi. Similarly, write assigns a value of local variable Xi to the data item X in the buffer block. Both these commands may necessitate the issue of an input instruction before the assignment. So transactions perform the read of X while accessing X for the first time. All the subsequent access are to the local copy. After the last access, the transaction executes a write operation. So example, this is an example. Here actually I have this is actually buffer block. So this is a disk block. So input operation. So what is input means? Transferring the data from disk into main memory, buffer block. That is main buffer block is available in main memory. So input means transfer the data from disk into main memory. Output means transfer the data from buffer block into secondary memory, that is a disk. So read of X, as I told, what is read of X means assigns a value of data item X to the local variable Xi. So assign the value of data item X into local variable Xi. This is a read operation. So whatever value available in X, that is assigned to Xi. Similarly, write operation. So what is write operation here is assigns a value of local variable Xi into data item X in the buffer block. It is a reverse. So that's what done here. That is a write operation. And Recovery and atomicity, modifying the database without ensuring that transaction will commit may leave the database in the incorrect state. Suppose assume that consider the transaction TI that transfers $50 from account A to account B. The goal is either to perform all data modification made by TI or none. This is actually atomicity. Either perform all or none. So here our goal is either to perform all database modifications made by TI or none at all. Several output operations may be required for TI, that is to output A and B. A failure may occur after one of these modifications have been made, but before all of them are made. There are two approaches are there. One is a log-based recovery and other one is a shadow paging. First one is a log-based recovery. So what is log-based recovery is, here the log is kept on the stable storage. What is meant by log means log is a sequence of log records and maintains a record of update activities on the database. So whenever any transaction TI starts, it registers itself by writing TI followed by start. So this is actually TI means it is a transaction followed by start. So this is a log record. So before TI executes write of X, the log record TI, X, V1, V2 is written. So here TI denotes for transaction and V1 it is a value of X before the write and V2 is a value to be written to X. This log record notes that TI has performed a write on data item Xj and Xj had the value V1 before the write. When the TI finishes its last statement, so we need to perform the commit operation. The log record TI commit is written. There are two approaches using the logs. One is a deferred database modification. Second one is an immediate database modification. First one is a deferred database modification. So this scheme records all modifications to the log but defers all the writes to after partial commit. So here we take an example. The transaction start by writing TI start record to log. A write of X operation results in log record TI, X, V being written, where V is a new value for X. Here actually no old value is needed for this scheme, unlike the previous one. Here the write is not performed on X, but it's deferred. So when the TI partially commits, that is TI commit is written into the log. Finally, the log records are read and used to actually execute the previously deferred writes. So this is actually the example. During the recovery after the crash, the transaction needs to be read if and only if both TI start and TI commit are there in the log. So this is an example. Okay, so T0, T0, this is a transaction 0 and this is a transaction 1. So here we are reading the value of A and we are deducting 50 rupees from the A, that is A equal to A minus 50, and then write of A. Then again we are reading the second value B and we are adding 50 to B, that is B equal to B plus 50 and write of B. And second transaction read of C, again we are subtracting 100 from the C and write of C. So this is a log as it appears in the three instances. First one T0 start, T0A 950, T0B 2050. First transaction, what we did is we are here we are doing the start. Then second one for on the B, that is T0 start, T0A 950, and here we are doing the commit. We are committing on T0 during the B. And again third one, again T0 commit, T1 start, C commanded, again we are committing. T1 also here commit. So if log on stable storage at a time of crash is as in this case, no redo actions need to be taken. For the first one, no redo action need to be taken. In the second case, redo of T0 must be performed since T0 commit is present. Third one, redo of T0 must be performed followed by redo of T1 since T0 commit and T1 commit are present. Second method is immediate database modification. So this scheme allows the database updates of an uncommitted transaction to be made as the writes are issued.